So welcome everyone, and this is Min-Hui. Today I will host the fifth webinars on the Digital Earth and webinar series on high-resolution land model and land atmosphere coupling. And this webinar series will aim to advance and the exploration and develop of high-resolution land models and land atmosphere coupling, and try to emphasize the significance of collaborative efforts. So this including the model intercomparisons on the high resolution land system models, and also this knowledge exchanges, what's the most advanced high resolution land models, the knowledge and the new physics that we'll share with each other. And most importantly, try to emphasize the importance of the integration of land surface process into the KM scale global climate modeling. So basically, this webinar try to establish a platform for the ongoing dialogue among the researchers focusing on the KM scale climate system models. So with a particular focus on the how the land surface process need to be improved when we go to the KM scale modeling. So today is our honor to have our fifth speakers, Junhong. Can you share your screen now?
Yes.
Okay.
Does it work?
Yes, thank you very much. So today is our pleasure to have Dr. Junhong Li, currently a postdoc researcher at the MPI, and then who is interested in the land atmosphere interactions within the storm resolving Earth system models. And his research explores questions such as like soil moisture conditions during the wet and dry, how this can trigger the precipitation in these high resolution models. And also he's interested in how the estimation of carbon stocks and flux in these storm resolving models. So Junhong, he graduated from Yonsei University in Korea in 2019. And after that, he moved to MPI as a researcher till now. So today, Junhong will talk about the weaker land atmosphere coupling in global storm resolving simulations. Okay, Junhong, it's all yours, please.
Thank you very much for a nice introduction, Min-Hui. And thank very much for having me in this honorable webinar. I am Junhong Li. I'm working at Max Planck Institute for Meteorology, Hamburg in Germany. My talk is about the land atmosphere coupling in global simulation at storm resolving scale. This work has been done with Kathy Hoeniger at MPI as well. And then this work has been published in PNNL this March under the name as the title. Okay, then let's talk about the talk. Land atmosphere coupling is mostly about soil moisture, precipitation feedback. So I only focus on that, not about the temperature. And then there are three main processes, how soil moisture leads to precipitation. That is, first, surface moisturing process, second, heating process, third, circulation. And then let me explain the surface moisturing process first. So that means the wet soil leads to larger evapotranspiration, and it provides water into the air. So it lowers lifting condensation level, LCL, so resulting in precipitation. In short, wetter soil leads to precipitation. So in this case, I can say there is positive soil moisture precipitation, so SMP feedback. For the second surface heating process, it means drier soil leads to higher sensible heat flux, and it warms the air. So the planetary boundary layer height increases, so it hits the LCL. So it creates precipitation. So in this case, in short, dry soil leads to precipitation. So there is negative SMP feedback. And the last, the circulation process. If there is soil moisture gradient, it can create circulation. For example, over the dry area, updrafting, updraft, and then over the wet area, downdraft. And then especially over the dry area with the updrafting, precipitation occurs. So in this case, I can say there is negative SMP feedback. If moisturing process is dominating, then the SMP feedback will be the positive. And then if the heating or circulation processes are dominating, then the resulting SMP feedback will be the negative. Then the question is, which one is dominating? So which the SMP feedback sign will be. But unfortunately, it's hard to tell because it's still on the debate. Since 2009, firstly, Kathy Hoeniger explored this problem, these issues, using two sensitivity experiments. First, with wet soil condition, and then she ran it with dry soil condition, and then take the difference of precipitation. And then if she found the blue color, meaning the wet soil condition will get more rain, or if she found red color, means dry soil condition will get more rain. Using this sensitivity experiment, she explores these debates. And firstly, with convective parameterization. She ran these two simulations with convective parameterization, and then she found mostly the difference is blue, meaning there is positive SMP feedback. And then this result is equivalent to the result from the GCM studies with convective parameterization. And then she ran these two set of simulations again with explicit convection in this time. And then she found mostly red color differences in precipitations, meaning dry soil gets more precipitation and negative SMP feedback. And this is equivalent to a limited area regional climate model result. Then naturally, the next question is, which one is really right? Actually, it's hard to tell because both approaches have their own limitations. For example, simulation with convective parameterization, it is really well known that the convective parameterization is too sensitive to the surface moisturing process than other two heating and circulation processes. With explicit convection, we usually run the simulation over the limited area. So the large scale process is missing, for example, like impact from the ocean or large scale circulation itself. And then because we don't have enough computational resource. Then what should we do? There is very easy solution, just running the global simulation at storm reserving scale. Very easy, huh? But it's impossible so far because we don't have enough computational resource. But fortunately, in our institute, and now even the other institute and center, they can run the global simulation at storm resolving scale or convection permitting scale. So with this valuable simulation result, I'd like to explore and compare the sign and strength of SMP feedback in the storm reserving simulations and low resolution simulations. And then if I found they are different, explore why. This slide is showing the simulation description or model descriptions. The model that I use is ICON model. The ICON is icosaedral non-hydrostatic model, which is developed by German Weather Service and Max Planck Institute. And then I use this ICON model and then with physics package developed by Max Planck Institute. And then I ran two simulations. First, I labeled as LR at 160 kilometer resolution with Kitka convective parameterization. And then I also used total turbulent energy turbulence scheme. And then I ran it for 60 years. And then I take only boreal submergence, JJA, for the analysis. For the second simulation, I named as SRM here. I run it at 5 kilometer without convective parameterization, and then with Smagorinsky turbulence scheme that I implemented before. And then at that time, due to the computational resource, I ran it for a year, and then I take JJA, boreal submergence as well. Using these simulation outputs, I check the sign and strength of coupling. For that, I use correlation coefficient, the Pearson correlation coefficient, very simple one. And then I use daily mean value of soil moisture and precipitation. And then at this point, you may wonder how I can confirm storm observing simulation is really different because you are just using 1 year data set. So it can be falling into the inter-annual variability of low resolution. So answer this question, I put little box on the right-hand side of my slide. In order to avoid this problem, I compute 60 value of correlation coefficient first for low resolution. Then I compute mean of them and one standard deviation of them. And then next I compute the correlation coefficient for some observing simulation. And then if its value is outside of plus minus one standard deviation of low resolution, then I assume it is okay, statistically significant. So I allow analyze for these points. Otherwise, I assuming it is falling into the inter-annual variability of low resolution. So I messed out as gray color. And then on top of that, if there is very small precipitation, is just making a noise. So I mess out where the precipitation is smaller than 0.1 millimeter per day. So the plot on the left-hand side is the example. You don't need to focus on the detail. I will explain later, but just look at this Sahara Desert or Central Asia is already masked out. So I don't analyze these points. So let's move on to the result part. Firstly, I look at soil moisture precipitation feedback, and then we found weaker, less positive, and more negative SMP feedback in storm reserving simulation than low resolution with convective parameterization. The plots are correlation coefficient between soil moisture and precipitation. Then I plot for the quasi resolution run for on the left-hand side, and the middle is storm reserving simulation, and then the right is their difference. If you look at the left one for low resolution, as you can see, the correlation coefficient is positive all the areas, and then you can see the hot spot over the Sahel region. But if you look at the middle in storm reserving simulation, this positive correlation is diminished almost to zero. And sometimes places like over Europe, even the sign is converted to the negative value. And then if you look at the difference map on the right-hand side, the storm reserving simulation minus low resolution, the difference color is almost red. That means storm reserving is less positive and more negative in the feedback. And then I wonder what if, because I'm using daily mean soil moisture and daily mean precipitation, it's because of just precipitation replenishes soil moisture. So in order to separate these signal, in this time, I computed correlation coefficient between soil moisture, but consecutive 9 days mean of precipitation. The plot on the bottom is the result. And as you can see, for the low resolution, there is no change. Still positive, even over the tile region is getting more positive. But in the storm reserving simulation, after I remove the impact of precipitation replenishes soil moisture, though the color are changing to more negative, meaning we have really negative SMP feedback in storm reserving simulation. Then I wonder what's going on there, why we are having different sign of SMP feedback. In order to look at furthermore, I separate soil moisture precipitation into two branches. First, soil moisture evapotranspiration feedback, and second, evapotranspiration precipitation feedback. I'm gonna discuss about the SMET feedback first, then move on to ETP feedback later. The result about SMET feedback, again, we found weaker SMET feedback for storm reserving simulations. The plots are the same as before, but in this time, I compute correlation coefficient between soil moisture and evapotranspiration. And then as you can see in low resolution, they are showing very strong positive correlation. But if you look at the middle, the strong blue color is getting weaker, so light blue, and sometimes still showing the negative value. And then this is also confirmed by the difference map on the right-hand side. Then we wonder why weaker SMET feedback in storm reserving simulations. In order to know that, we compute mean average of correlation coefficient between soil moisture and evapotranspiration based on soil moisture index. We plot storm reserving simulation in blue color, of red color for the low resolution. And then I found the two lines are overlapped very well. And this is really not surprising because we are using same atmospheric model and same land surface model. So that's why they behave same given soil moistures. Then why they are different? Then I check histogram of soil moisture. Then I found low resolution simulation has more drier soil than storm reserving simulations. Here, the red boxes is histogram of low resolution. And then for the low resolution, it has very dry soil. And in the dry soil, we are in the water limited regime. So that's why we are having higher correlation between soil moisture and evapotranspiration. But in the higher soil moisture or storm reserving simulation, it is usually in the energy limited regime. So there is small relationship between soil moisture and evapotranspiration. So that's why we have weaker, less positive SMET feedback in storm reserving simulation. Let's move on to the second point, ETP feedback. And then again and again and again, we found weaker, so less positive, and more negative ETP feedback in storm reserving simulations. The plots are the same as same again, and then we compute the correlation coefficient, ET and P. If you look at the left-hand side, there is positive area and the negative area, but it is getting more negative in the storm reserving simulations. I would say negative now is more dominating than positive in the storm reserving simulations. And then if you look at the difference map, now the difference is biggest ever we saw in other plots. So yeah, more negative ETP feedback in the storm reserving simulation. Then I wonder why, again, and then we made two hypotheses. First, low resolution simulation is too sensitive to moisturing process. Second, storm reserving simulation is more sensitive to heating and circulation processes. So what that means is, as I show you at the beginning, surface moisturing leads to usually to ETP or SMP positive feedback. But for the surface heating and circulation, it usually leads to negative feedback. So we are assuming low resolution is emphasizing the surface moisturing process. So that's why it's showing a positive feedback. For the storm reserving simulation, it is emphasizing the other two processes, heating and circulation. So that's why we are seeing more negative feedback. For the first point, it is already shown by many other studies. For example, here the plot I took from Keller 2016. In his thesis, he showed how precipitation behaves with convective parameterization as a time series. He plotted precipitation in blue color here. And then what he explained here is when sun rises, evapotranspiration increases, then convective parameterization detects that surface latent heat flux or evapotranspiration. Then it triggers precipitation. And then it turns it off right away. So that's why there is a very small peak at the beginning. And then this rain order will replenishes the soil moisture. So the evapotranspiration increases again. Then the convective parameterization turn on the precipitation again. So that's why there is a second peak. And then it repeated during the daytime. So there is very many peaks of precipitation. Then obviously this is not really realistic. So, and then it's designed for convective parameterization. So we shouldn't use it. In order to check the second point, I plotted the mean average of precipitation based on evapotranspiration. And then as I did, I plot storm reserving simulation in blue, low resolution in red. And as you can see, in low resolution, precipitation is linearly increasing with evapotranspiration. But that's not really true for the storm reserving simulation. It seems like at the beginning, it looks like linear relationship, but after 2 millimeter per day, the linear relationship has broken, and it seems like on a non-linear. We are thinking this is indirect evidence of the surface heating process or circulation process work on it. And then we want to check furthermore. So in this time, we plotted mean average of correlation coefficient between ET and P in solid and correlation coefficient between sensible heat flux and P in dashed line. And as you can see in low resolution, it is usually low resolution have higher value for TP feedback than storm reserving simulation. And there is almost zero or very close to zero correlation between sensible heat flux and precipitation correlation coefficient. And then there is a, and then I wonder furthermore, it's really because of the convective parameterization or not. So to confirm that, I analyzed two set of simulations at storm reserving scale or convection permitting scale. The first one is the simulation with convective parameterization using IFS model from ECMWF. Second, the simulation with explicit convection using ICON model from MPI. I plot the correlation coefficient between soil moisture and precipitation for two simulation results. And then as you can see for the IFS result, it is still showing a positive correlation coefficient. But if you look at the middle for icon, the positive correlation coefficient is less bluish now. And sometimes the sign is converted to the negative over the euro, for example. And then the difference map are showing very red. So once again, it is confirming why we have weaker coupling is about explicit convection, and why the low resolution run is showing a strong positive. It's because of the convective parameterization. So I'm really happy about this result. So I move on to the last part. I wonder, our finding weaker coupling in the storm reserving simulation is really realistic, or they just behave differently because we are missing something in the model. So in order to know that, I computed the correlation coefficient, these three correlation coefficients, again, using the FluxNet 2015 data sets. So the top is SMP, middle SMET, and the last is ETP feedback. And then I plot the observation in gray boxes. And I only take the sites where have the data set more than 10 years. And then I interpolate the simulation result, two simulation results to this the FluxNet sites, and then plot the low resolution in red colored boxes, and then plot the storm reserving simulation on in blue dots. And if you look at the just top panel, the usually observation is very close to the zero, or sometimes they are showing negative value, for example, here and here. And then storm observing simulation result comes after, then low resolution. And low resolution simulation always showing very positive value for SMP. And the other two feedback also showing the similar result. And then I wonder, just to increase the number of the site, in this time I plot the whole site available for the analysis. And then I change the color of the site name into blue if the storm reserving simulation is closer to the observation, and then colored red for if the low resolution is closer to the observation. And then I count the number of the site. Then we found more than at 70% of the site are showing storm reserving simulation is closer to the observations. So with this very lucky and then happy result, I'd like to summarize my findings. We found the land atmosphere coupling is weaker and more negative in the storm reserving simulation than quasi resolution, and we confirmed this with observation. And then I'd like to say two implications from our study. The first one, maybe it's too bold, but the increase in frequency and strength of droughts and heat waves under climate change estimated from low resolution with convective parameterization is too strong. And our second point is precipitation over the Amazon is more resilient to deforestation than previously we thought. Before move on to the last slide, I'd like to discuss the second point one more time, because my colleague Arim Yun and Kathy Hoeniger at NPI already have had a look at it. So they explored the Amazon deforestation response in storm reserving simulation. They ran two simulations, first with just normal condition, and second, they deforest the area surrounded by this red contour in the plots. Then they remove the forest and then replace it by the grassland. And then the plot on the B and D are showing the evapotranspiration differences in dry season and wet season. And if they found brown color, that means the evapotranspiration is diminished in the deforestation simulations. And they found a diminished value for the two seasons, dry and wet seasons, but they don't find change in precipitation in terms of domain average precipitation. But they only found that precipitation difference only has changed. For example, in dry season, precipitation increases over northern part of this deforested area and decreased southern part. But in the wet season, precipitation increases southern part, but decreases over at the northern part. But the average value doesn't change much. I think this is very interesting result, and then it is really connected well with my study. So I'd like to just show you this result. This study is on the review now. On the name, the title is Muted Amazon Rainfall Response to Deforestation in a Global Storm Reserving Model. So if you are interested in that, please wait. I guess it will be published very soon, I will say. So please have a look at it. Thank you very much for listening. I'd like to have a question. Thank you very much.
Well, thank you very much, Junhong, for these nice presentations, and it's clear. And also later you show that how this have some implications for the land use change impact. That's quite interesting as well. Great, and so if you have any questions, please post your question on the Q&A. And I saw some of the questions from the Q&A sections. Junhong, can you see?
In the chat, you mean?
Those, not in the chat, but there is another box. Another item is a Q&A. Can you see it? And there is 3 questions over there.
Okay, yeah, that now I can see it. Yes.
Okay. So yeah, can you read it and then also try to respond if possible?
Okay, I'll try that. So first question is from Paul. He asked about the. Okay, let me go to this slide first. Okay, yeah, he asked about the scale mismatch. Yes, I average first for the to match the. Let's explain this way. I first interpolate the data into 2-degree boxes first, and then I compute the correlation coefficient. So so the both low resolution and then storm reserving scale simulation are interpolated into the 2-degree boxes. Then I compute the correlation coefficients. So I would say scale mismatch is okay for that. And then also I'd like to say I also computed the other way around, but the main results are the same. Okay, I'm not sure it answers the question, but I will move on to the next.
Okay, yeah, Paul. Oh, okay, I think he responded.
Okay, thank you very much.
And the second question from Liz. Yes, please, Junhong.
Yes. Okay, let's move on to this. Yes, just correlation coefficient is impossible to disentangle. Soil moisture leads to precipitation, and precipitation leads to soil moisture. But I also concerned about that. So that's why I do the additional analysis like this. So in this time, if you look at the bottom plot, I computed the correlation coefficient based on soil moisture, but consecutive 9 days of precipitation. So for example, at the first day of soil moisture are computed with the 2nd to 10th day of precipitation. So it can remove, yeah, it's hard to remove all the signals, but at least some signal from the P leads to soil moisture signals. That's what I did.
Okay. Okay. Yeah. And the from Chihiro, can you see the third question?
Yes, I can say
about
I can see the
about
question,
the
yes.
soil moisture in icon model.
Yes. Yes, I also concerned about the soil moisture initialization. Yes, because as you can see in this slide, for the storm reserving simulation, I ran it only 1 year. And then I check whether the soil moisture is really calibrated or not. At the first 4 months, it seems like until 4 months, I would say, put it this way. So until May, it seems the soil moisture reached the equilibrium, except the bottom soil layer. So typically root depth is already inside of 3rd or 4th depth. So I assuming it's fine to analyze the data set. That was my decision at the time. And then afterward, we have more computational power. So we can run 30 years using at a storm reserving scale at 5 kilometer. Then I check also the soil moisture initialization. And then it also shows already after 5 months or 4 months of the simulation start, the soil moisture reached the equilibrium except the bottom part. But I guess the bottom soil layer is not really, I mean, in the short term, like 1 year or 2 years, it's not really important for the land atmosphere coupling perspective, I would say.
Okay.
Okay, then.
Okay, cool. I think he also responded. And Sasha? What source code change can we make to run low resolution models to make them more like SRM models?
Well, it's very, very difficult question and good questions. I think the main differences between low resolution and high storm reserving simulation or high resolution is the convective parameterization. And then I would say the design of convective parameterization made to very sensitive to the surface moisturing process. So maybe we explore these issues more and make it as sensitive to the moisturing or heating at the atmosphere, not the surface itself. Maybe it will really alleviate the problem a bit more. But of course, running high resolution is very beneficial. For example, like convective alone can consider the horizontal entrainment and mixing process. Maybe I assuming it's better representing the convection itself. So that is not really impossible. That cannot be considered by low resolution itself. So my suggestion is just changing or improving the convective parameterization.
Cool. And the next one from Chris Taylor. So it's about link to these with more years of data, can you statistically isolate the impact of persistence from land atmosphere feedback? Junhong, can you, yeah.
Yeah. So let me check. Okay. Yes. Well, So I'm starting to look at the long-term simulation result. So at the moment, I really cannot say something on that, but I believe we can isolate. And then my next plan is applying the Chris-Taylor method to also look at these long-term simulations, whether I can also see some mechanisms and then also the persistence impact. So that's my plan. I am not sure that answers the questions, but if you let me know,
Chris,
it's yeah.
Yeah, okay. Chris, if you have any further question, please respond. Okay, then let's move on to Joshua. Can you see the message?
Yes, I can. I'm reading
Okay.
it.
Okay.
Yeah. Okay, so I need to show this plot, I guess. So our guess is it's just because of negative SMP feedback in the storm observing simulations. So generally it means as storm observing simulation tends to homogenize the fields. Like if there is a dry patch, then precipitation moves that field and then fills up the soil moisture. And then the other part are dried out. Then the precipitation moves onto that and then also fills the soil moisture. So that's why we are thinking soil moisture is generally increasing. But in the low resolution simulation, the dry region are getting just dry and wet region is just getting wet. So that makes the differences. For the second question, so we are thinking due to the same negative SMP feedback, so I would say the soil moisture is getting increased, even if we started the simulation dry state. And then the other work from Kathy Weniger, she also explored the land precipitation versus precipitation over the ocean. Then she found land tends to drag the precipitation water from the ocean. So I would say even if we started the dry soil, after we get the equilibrium state of soil moisture, it will be wet soil than low resolutions. That is my thinking.
Okay, cool. And the next question is about his sec. Why 2 degrees? Boxes.
Oh, yeah. Why 2 degrees? We first, let me go back to model description. First, because I ran the low resolution simulation at 160 kilometer, which is just typical GCM resolution. And then also there is a paper that discussed the scale to look at the land atmosphere coupling. And then if we look at this land atmosphere coupling smaller than grid size, like 1 or 2 degrees, then we are missing the system that is moving. For example, MCS are moving, right? And then if we are just considering smaller than 1 or 2 degrees, then MCS can move after 2 or 1 days, even within the day. So I don't want to miss that behavior or I mean the system. So that's why I choose larger grid size for the analysis. And then I guess the next question, have you calculated the circulation noise? No, I didn't really check, but I want to. So my next topic, and then what I'm really interested in that is what really makes the difference. Is it really, I mean, how many times it's related to the surface heating, or how many times it's related to the circulations, or also the moisturing process. So maybe it's a good idea to look at the circulation anomalies. And then also I checked the radiation. What I remember is radiation is smaller for the low resolution in general, but not that big different. But I guess it's because of the frequency of the precipitation. And then this is also due to the convective parameterization. In the low resolution simulation, it precipitation a lot, almost every day, but that's not true for the storm reserving simulations. So it makes some differences on that. There is an additional comment, right?
Yes. Can you see it? The slow motion feedback.
Yes, yes. So maybe I can move on to the plots. So this is, I think, the main process, like, let's go back to here. So the resulting sign of SMP feedback is determined by the competition between these three, I would say. Of course, there will be the more, but let's pick the main processes. Sometimes moisturing is dominating, sometimes heating and circulation are dominating. And the region where still are showing positive in the storm reserving simulation is because moisturing is still a bit stronger than other two. That's my interpretation. So that links to my second topic. So how many ratio between them? How much they are happening than heating or circulation or moisturing? That is my next question.
Okay, so you will try to quantify.
Yes, basically.
Okay, the magnitude. Okay, and the next question is about GPU.
Okay.
Technical question.
Yes, that's really interesting. When we developed the icon model, we made it possible for the GPU, but for this simulation, we only use CPU, but we can run it on GPU as well. Actually, we are in our institute, we have very different projects. Few of them are really technical. For example, like running 5 kilometer or 2.5 kilometer, even 1.25 kilometer simulation on GPU. But my answer on the question, for my simulation, we ran on CPU.
Okay, cool. And the next question is from Liang. The coupling strength between the icon and low resolution with other CMIC6 models.
Yes, I did. I compare first with MPI ESM and then also other AMIP simulations. And then they are still showing very positive, very different from the storm reserving simulations.
Okay. And next question from YouTube about quantifying the relationship between slow motion and precipitation with the correlation coefficient. Because slow motion P and does not have a linear relationship. So any comments?
Yes. Yeah, they are not apparently have a linear relationship. Yes, I agree. Yeah, I would say the limitation of my study will be the method that I use to measure the correlation coefficient. I mean, the feedback. But I tried different methods. First is maybe I have the slide. Maybe I can go to that. Yes, this one. I use Chris Taylor method to compute whether it is statistically really negative feedback between soil moisture and precipitation or not. So I compute also for the storm observing simulation for my analysis. And then it is clearly showing there is precipitation when statistically soil is dry than usual. So the red color means that. If the blue color is showing, that means precipitation occurs when there is statistically wet soil. But in the storm measuring simulation, the color is red, so it's perfectly aligned with my finding with the correlation coefficient. So so far, I guess my finding is still valid, even if there is some complexity. But also, I want to explore with other metrics later. For example, the method proposed by Paul Dormeyer. So yeah, that's my next plan.
Okay, cool. And Adrian has questions about quantifying the spatial inhomogeneity of so much neutrino simulations.
Okay. So when I said about the homogenize the field of soil moisture is I said regarding the general large scale pattern. But if I look at the 5 kilometer resolution in raw resolution, I still see very strong variance between the grid cells. And then also I quantify the same the preference, like this plot. For this plot is showing just temporal preference, but I also check for the spatial preference and then also homogeneity preferences. And then it is also clearly showing very precipitation prefers inhomogeneous fields of soil moistures. So, but I'm not sure I really answered the question, but please let me know.
Okay. Okay, and the next question from Jun about because Goulet in 2015 shows this positive temporal coupling.
Yes, my answer is no, we didn't really look at the observation of satellite yet, but I love to because yeah, it's really interesting.
Yeah, I think it's good to compare. Yeah.
Yes, indeed. We only choose FluxNet sites, but you know, it's just point sites. So if I can use satellite data set, it would be very nice to look at the spatial patterns as well. Yeah.
Okay, cool. And next question from Kristen.
I guess she's saying this plot, right? Like, okay, I guess it's a similar question that I had before. So why still the storm observing simulation have this, even if it's small but positive, is okay. It's because still moisturing process are dominating over heating and circulation at that point. So let's say like moisturing process is dominating like 60%, and then heating is 40%, then it will be still positive, even if the magnitude is still very small.
Mm.
And then even if we are having explicit convection, still there is a condition that surface moisturing process leads to precipitation. So that's why I think. But in the quasi resolution with convective parameterization, no matter how the atmospheric profile is or surface heating or moisturing, the model is just trigger the convection with the evapotranspiration. And that's why it is showing very positive.
Okay. Yeah, I think this address Christine's question. If not, please. Okay. And I think I saw some questions over the chat box.
Okay.
But I think some of them, I think already you answered during the Q&A.
Mm-hmm. So.
And I think, well, I think you have.
Yeah, I guess. But did I answer Liliana's question?
Yeah, no. How many years did you use in your analysis?
Oh, okay.
I think you mentioned that, right?
Yeah, for the low resolution, I use 60 years. And then for the storm observing simulation, I use 1 year. But afterward, I published a paper, I analyzed 5 years and more than that. Also, they are showing still negative, and then the result is consistent.
Oh, okay. So later on, you have 5 years of JJA, you mean?
Mm-hmm.
Okay, cool. Thank you. And I saw one question, one people raised their hand. Toshi, do you want to ask question now? Can you hear me?
I think I will
Hey,
allow her to speak. Let me see. Okay, still on. Okay.
Can I speak? Okay, cool.
I have allowed her to speak. I've allowed Ashutosh to speak. I'm not sure if he can hear us.
Ashutosh, can you hear us? I guess the mic still mute. Well, I think it's almost 1 hour, so I think maybe I will. Okay.
Before we close the session, Chris mentioned one more thing. So he said,
"Oh, okay.
Yeah, Kirsten's question is also why we still have positive. It's because we include persistence effect. Yeah, sorry to forgot to mention that. Yes, that's correct. Yes.
Yeah, the persistent effect is critical over here. Yeah.
Yes.
Okay, great. Well, thanks, Junhong, again. Well, a lot of discussions. Well, that's pretty nice. And it's always that within this webinar series, always a lot of discussions. This is critical for this community, try to have more people join to discuss this high resolution land model and then atmosphere coupling. So, and this is a bi-monthly webinar. So we will have next one usually it's the first week of October. So everyone is welcome to join. And so I will close today's webinar. Well, Junhong. Thank you again. Thanks very much.
Thank you very much. And thank you for the
Okay.
comments and questions.